I would like to give a brief introduction to Planck units. First, I will explain how they are derived and how conversion to other units works, and then why they are actually useful. Planck units are a special case of natural units that arise from natural constants, and they work under the assumption that 5 natural constants are all set to 1. But what do I mean by set to 1? Let's consider an example and set c equals 1. c, being the speed of light, consists of a numerical value and a unit, and together they are set to 1. Think about it like that. We can always express a given speed as a fraction of c. If I'm given a value of about 120 million meters per second, I can write it as 0.4 c. Now we replace the c by 1 and we get a dimensionless number. There's information lost in the sense that you cannot say which quantity the value of 0.4 describes, but the moment you tell me that 0.4 is a speed, I can say, alright, a speed would be meters per second in SI units, and a constant c can be expressed in these units, so we'll do just that and multiply by 0.4. Another way to write out what I just said would be to write the numerical value with units and multiply by c over c. Now we express the c in the denominator in the same units as our numerical value, and we obtain a dimensionless number times c, which we set to 1. This conversion only works if the person who converts from SI to natural units and the person converting back are using the same natural constant. If one has the speed of light in mind, while the other person is thinking of the speed of sound, this will not work. We have to agree on all the constants we use. Anything else would be redundant. For Planck units, the speed that is used is the vacuum speed of light. So we're now able to convert speeds to Planck units and back, but what about length, time, and so on? We now have to use the other 4 constants, and we will start off by some dimensional analysis on all 5 constants. I will denote dimensions by their respective SI units, since they are better known than the symbols for the actual dimensions. The discussion can of course be generalized to any system of units, but we're mostly interested in the conversion from and to SI units anyway. By dimensional analysis for the constant c, we find length over time, or as I said in SI units, meters per second. For the gravitational constant g, we find meters cubed over kilograms seconds squared. For the reduced Planck constant, h bar, we find joule times second, which is kilogram meters squared over second. For the Coulomb constant, we find kilogram meters cubed over second to the 4 ampere squared, or meters cubed kilogram over second squared Coulomb squared. Technically, ampere would be the SI base unit, but for Planck units, the dimension of charge is used, and assume the base unit for now. Finally, for the Boltzmann constant, we find meter squared kilogram over second squared Kelvin. Combining these constants by multiplication of various powers of the constants allows us to obtain expressions whose unit is any combination of the 5 base units used. Most importantly, they allow for expressions whose unit exactly corresponds to one of the base units. This works out as with exactly 5 base units that we would like to express in terms of exactly 5 constants, and because none of the constants can be expressed in terms of the other 4. This is similar to elements on a linear vector space being linearly independent. So we find combinations of these constants whose unit is exactly one of the base units mentioned. For instance, if you take h bar times g divided by c cubed all in SI units and take the root of the whole expression, you end up with a quantity that has some numerical value, whose significance we're yet to discover, but most importantly, a dimension of length and a unit of meters. Similar expressions can be found for kilograms, seconds, Coulomb, and Kelvin. Converting a quantity from SI units to Planck units now works just like before. Write down the quantity in SI units and multiply by the expression for that unit and its inverse, effectively multiplying by 1. We didn't change the quantity by this. Now remember that we would like to obtain a dimensionless number, so take the inverse factor and write out values and units of the constants in that factor. Doing the calculations will cause the units to cancel out and the numerical value to change. What we are left with is our dimensionless number times this factor containing all the constants that are now set to 1, so the factor simply vanishes. What's left is our result in Planck units. In principle, every quantity can be converted like this, but more importantly, it allows us to find conversion factors for the base units. Conversion factors for any combination of these base units are then exactly the combination of these conversion factors. For example, as the Planck length equals 1.62 times 10 to the minus 35 meters, and the Planck time equals 5.39 times 10 to the minus 44 seconds, the Planck speed equals about 300 million meters per second, the vacuum speed of light to be exact, which is not surprising at all since it is the very constant we used and set to 1. All the conversion factors can of course be looked up, but it's good to know where they come from. By choosing the quantity on the left so that we obtain exactly 1 on the right side, we obtain expressions for the Planck base units in SI units. For example, let's write L sub p for the Planck length in meters and demand it to be 1 in Planck units. The first factor is set to 1 as it was before, and the second factor can be brought to the other side of the equation. We obtain the back conversion, the expression of the Planck units, length in this case, expressed in SI units. They are simply the combination of constants that we found to have the correct dimension. Now their numerical value makes sense as well, as it is simply the factor for conversion from Planck units back to any other unit system as long as we express the constants in that system. So we obtained factors to convert quantities from arbitrary, but preferably SI units, to Planck units, and back again. Other units that are a combination of base units, like meters per second for speed, work by just combining the conversion factors in the same way. And of course the back conversion factor is just the inverse of the conversion factor, and vice versa. That is all very nice, but one question remains. Why do we do this? Well, SI units are great, but they are arbitrarily defined. For instance, the meter is defined as the distance which light travels in a certain amount of time, but that amount of time is arbitrarily chosen. As a result, these nasty constants arise in various formulas where they contribute nothing but compensate our poor choice of units. Newton's gravitational law, the mass-energy equivalence, the energy-momentum relation, Coulomb's law, and many more, especially more complex expressions calculated from these, are shorter and somewhat more elegant if we set our 5 natural constants to 1. The equations obtained, however, only make sense if one has Planck units in mind. Take Newton's gravitational law for example. To obtain a meaningful value for the gravitational force, we have to convert both masses and the radius to Planck units. We insert them into the formula and obtain a dimensionless number, the force in Planck units, that we can now convert to any other unit as we like. So if this unit system is less arbitrary than the SI system, why is it mostly used for theoretical applications? Well, first of all, you lose the power of dimensional analysis to check if equations are correct, and if at one time you forget which dimension the quantity you're dealing with should have, you are completely lost. Second, the numerical values obtained are very impractical on the scale that most of our life happens at, while SI units, or at least meters, seconds and kilogram, are much clearer to us. There are also many more unit systems that are more or less useful in certain cases, but natural units, and as a special case Planck units, are unique, and I hope that you now understand them a little better. We can therefore write the time as an infinite series. If we did everything correctly, this series needs to converge, since the clock hands do overlap in a finite amount of time. And in fact it does. It is a simple case of the geometric series and there is a formula for it.